So in this part, we will start thinking about designing matching networks. And I will start by having a very basic definition of a matching network. So as we discussed before, a matching network is essentially a load. It's a network that takes a load to a desired value. So what is the desired value? So in general, you will have some type of a load impedance of R plus JX, and some type of a load of a source impedance ZS. And as you very well know from matching theory, even from your undergraduate courses, the whole idea here is that maximum power transfer occurs when ZS is equal to ZL complex conjugate. So by definition, a matching network is a device that allows maximum power transfer from the source to the load. Now, often it happens that my ZS is equal to 50 ohms, and that means that I'm trying to match ZL to 50 ohms or to the center of the Smith chart. And that's the type of matching we have discussed so far, and that's actually quite commonly done because ZS is 50 ohms. But I don't want you to think that that's the real matching. The real matching is always when ZS is equal to ZL complex conjugate, and that's important because a lot of times ZS is not 50 ohms in real life. So if I'm looking at this matching network from this point of view, what is really important to realize is that I'm designing the matching network to either bring my ZL to have a value of ZS complex conjugate. That's one way to think about it. Or another way to think about it is I'm bringing my ZS to have a value of ZL complex conjugate. So either of these two transformations is possible, and there was actually a question last time, how do I design a matching network? And so here's basically the way to think about it. Either you start from the point on the Smith chart that represents the load, and you move this point such that you hit ZS complex conjugate. Often that's 50 ohms, but not always. The center of the Smith chart, in other words. Or you pick your ZS and you move it to a point on the Smith chart that is equal to ZL complex conjugate. Either of the two are basically equivalent. The vast majority of people are thinking of this way, from the load to the generator, because again, a very often scenario is that ZS is 50 ohms. So it's easier to move from a random point of the Smith chart towards the center rather than picking the center and trying to move basically to ZL complex conjugate. Now, what are the main requirements when you design a matching network? I have actually listed here a few, and so I'm going to go ahead and discuss some of them. Probably the most important requirement that most people think about immediately when they think about a matching network is that it must have a low loss. Because if you end up consuming 80% of your power into the matching network, even if you achieve perfect matching, it's pretty useless. However, low loss often means reactances only or transmission lines. Now, it's easy to say that, it's much harder to do. So matching networks basically do have losses. Depending on the application, low loss could mean anywhere from a loss of half a dB to maybe 1 dB. But if you start having more than 1 dB, most people don't consider this to be very low loss. That's about 20 or 25% loss of your power. Now, also, it's not very helpful if your matching network is the size of this room. Then most people won't be able to use it, and so you have to fit it reasonably well into your system, and of course depends on what your system actually looks like. Bandwidth is a huge deal. There is a very famous Bode-Fano criterion, which is in the book, but we're not going to discuss it in detail in this first part of the course, which actually gives you a trade-off between performance and bandwidth. So you can't have a very wide bandwidth without sacrificing performance, or it's actually easier to get really good performance for a narrow bandwidth. And that's a fundamental idea of networks. Tunability is coming more and more into the picture as we're talking about smart or adaptive communication systems. So that means that my matching network should not only work at the frequency I designed it today, but I should be able to just push a button and shift it to a different band. Power handling is very important, particularly when we talk about matching networks for transmitters. If I'm designing a radar that's supposed to send out 10 kilowatts, I'd better be able to have a matching network that won't burn at 10 kilowatts. Linearity is a huge issue as well. We have talked about linearity in the beginning of the course, but if I'm sending basically a single tone here, I really insist on a single tone towards the load, not multiple frequencies hitting my load. Of course, somebody has to be able to manufacture this at a reasonable cost. And speed and power consumption also come into the picture. Speed comes in cases where you have tunability, so they actually goes hand in hand with tunability. Power consumption is a big deal, particularly if you, again, tune the network. You don't want to spend too much power when you try to tune that network. So there isn't really a single technology or a single approach to hit all of these requirements or additional ones that may exist in this application, but it's very important to keep all of these requirements in mind. It's really easy to hit just one of those or two of those and forget about the other ones. In real life, all of them have to be done at a reasonable level.